Welcome to New Line 99. This time we are again exploring arithmetic in assembly language, but this video is specifically about floating point math. In our previous video we looked at integer math. Be sure to check out that video too if you missed it. Assembly gives us access to floating point arithmetic. But how do we represent floating point numbers? Decimal numbers are usually comprised of a series of numerals and a decimal point somewhere relative to the numerals. In floating point math, the position of the decimal point is called the exponent. The numerals together are called the mantissa. So in computing, floating point numbers are stored as these two constituent parts together. On the TI-99, the floating point number is stored in an 8-byte space in a data system called Radix 100. In this format, the first byte is the exponent, and the remaining 7 bytes hold the digits of the mantissa, left justified, and each byte holds 2 digits of the mantissa, so that each byte has the value between 00 and 99, giving us 100 possible values for each position, hence the 100 in the name. In fact, the term Radix 100 means that it's a base 100 numbering system. When we're working with floating point numbers in assembly, we can't just use the same operations that we use for integers. The CPU does not have native floating point operations, so the way floating point math is achieved is through a series of library routines. We hook into 2 utilities, one called XML-Link that gives us access to calculations, and one called GPL-Link that'll help us take the values, convert them into strings, and do lots of other cool stuff. XML-Link is not related to XML as an extensible markup language. It's probably something more like expanded memory something, married ladybugs, who knows? They don't say. Anyway, it's a link to a library in ROM with several math operations. We first copy the 8 bytes of each floating point number we're working with into parameter space called FAC and ARG, and those are the floating point accumulator and additional arguments. And at that point we're ready to call the routine, followed by 2 bytes of data that identify which arithmetic operation we want to run. There is addition, subtraction, multiplication, division, floating point compare, value stack versions of all those operations, string to number conversion, floating point to integer conversion, and integer to floating point conversion. The value stack versions of the operations pull the first parameter from the specified address in VDP and calculate it against a floating point accumulator. GPL-Link, which is Graphics Programming Language Ladybug, is a library with several additional functions. There you'll find floating point number to string conversion, greatest integer, involution, which is powers basically, square roots, exponents, natural logarithms, sine, cosine, tangent, and arctangent. In addition to the FAC and ARG addresses, there's also an error address that contains a return value as well, that can tell us if an error occurred when the routine was run. If we overflow the accumulator, divide by 0, try to get square roots of negative numbers, that's where we'll find out. Floating point math on the TI is done entirely through code rather than on the chip, so it's pretty slow. So only use it when you really must work with floating point numbers. A word of advice. It's good to keep the editor assembler reference manual handy when working with floating point math. These operations put values in some weird places. We'll do a simple example of floating point math. Let's say that we want to show 2 decimal numbers, multiply them, and then display the resulting value. We'll make 3 8-byte data buffers for the calculation. The multiplicand, which will give the value 914.21. The multiplier, which will give the value 3.8077. And the product of multiplying the two, which we won't give any initialized value, just an 8-byte block. Let's identify the addresses where FAC and ARG are in memory. These addresses are listed in the Editor Assembler Manual, page 259. The last piece of information that we need to keep, specifically for converting numbers to strings, is really silly. Page 255 of the manual reveals that the FAC plus 11 is the least significant byte where to find the output string, which is the most significant byte, 8300, implicitly. So that means we have to find the location of the string by moving that one byte at the accumulator plus 11, swap it to the low byte, and move hexadecimal 83 into the top byte. Yeah, that's right, they couldn't spare the extra byte and just store the whole 2-byte address somewhere. They had to make you waste 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes of memory building the address. Do they think we're okay with that? Yeah, I guess we're okay with that. Well, here we go. Let's make a subroutine to display a floating point number on the screen. For input, R0 will be the VDP address for the screen position, and we'll make R1 the address of the floating point number. We copy the 8 bytes into the floating point accumulator, and then call GPL link routine hexadecimal 0014. Now, here's that silly thing we have to do to get that string location from FAC plus 11. Move byte, swap bytes, move byte. We get the string length from FAC plus 12, and we're ready to send the string to the screen and return. Let's calculate the multiplication in a subroutine called calc. The inputs are going to be the addresses of the two numbers we're multiplying in R0 and R1, and the output, the result of course, with the address in R2. We copy the operands into the FAC and ARG, call XML link, followed by the data indicator for multiplication, 0800, copy the new FAC bytes into R2, and return. Now that we've done all the heavy lifting, the main program is simple. We'll print operand 1 at 004D, which is kind of in the top middle of the screen, and operator 2 at 006D, the line below the first one. Load the addresses for operand 1 and 2 and the result. Do the multiplication, and print the result at VDP address 00AD. We'll throw in an asterisk and an equal sign for cosmetics, loop the end, and we're ready to test it out. And we get the answer we're looking for. If we wanted to add the two numbers instead, we can just change the data value after XML link to 0600. And of course, we change our cosmetic asterisk to plus. Now it's addition. Subtraction would be data 0700. Division would be 0900. That's all we're going to do now. Hope to see you again when the assembly series continues. Catch you next time from New Line 99.